Good morning. I am Mr. Ish. A very cold morning here in Minnesota. I welcome you all to this very warm and interesting video on volumes of revolutionary solids. We've never presented this in a formal sense, and in this video we will do so, and let this be that video where we talk about solids of revolution. These are the true revolutionary solids, which are located a distance away from the line of axis, or the line of rotation as you want to call it. Take this instance right over here. We have an xy axis specifically drawn over here, and we just have a specific area region of the curve which is presented by this shaded area. If you were to just rotate around this y-axis, if you were to do this rotation, and this right here would be a true rotation, you'll get a solid which will look very much like this. We don't have to be too fancy here in our artwork, but you can see there's a true rotational effect. Why is that? Because this point right here remains fixed on the line of axis, and that point is very well noticed here. A point like a spinning top which stays fixed as the object or the curve or the region rotates around a line of axis. This right here is a true rotational solid. If you take the same representation, we have something drawn like this, and now the line of axis has been pushed away a distance, and you're doing a rotation around this. You want to call it a rotation or a dynamic movement, or you can even say a revolution. In this instance, you'll get a true orbital movement or a revolutionary movement, and that's why we like to call this, or I like to call this, a solid of revolution, a true solid of revolution, because now when you do the representation of this in terms of a image that develops a three-dimensional solid, you have all of this space which is open from here to here. It's all open space, and then from here to the top it's a wider open space. But you can see there's a revolutionary movement here. There's no fixed point along this line of axis that stays put in its place as a movement occurs. Here, this specific point stayed put in its place. Here, there's no point. Everything is translating in a circular movement about this line of revolution, if you want to call that. So we're going to be looking at the volume determinations of solids of this form, not of this form, where the region is located at a distance away from your line of movement. Our first question for this video is seemingly straightforward, something I've alluded to earlier in this video. We have a single function over here, y equals root x, but we have two equations, the other one being x equals 1. We have a movement or a rotation, revolution, as you might want to say it, around x equals minus 1. Y equals root x is a radical graph. X equals 1 is a vertical line, and we have this region of space which has been bound by these two curves. X equals minus 1 is this line of rotation. You want to do a good solid representation, we can. It would look something like this. Here's my line of rotation, would be right over here. Nothing is drawn to scale over here. It would be something like this and something like this. You would have a solid generate over here, a revolutionary solid by all accounts. Everything revolving, orbiting, circulating around this x equals minus 1. There's no point which will stay firmly bound in place. Everything is in a circular path. And when we're looking at this in terms of a cross section, you slice this out, you're going to end up having a washer develop. And everything around this washer has to be analyzed with regards to this central rotational line or revolutionary line, x equals minus 1. We'll have an inner radius to worry about and an outer radius to worry about, but everything is measured here not from a x and y axis, but from a vertical line here. The inner radius is going to be measured here from right here. This line of rotation to the very first curve, that's my inner radius. And you're going to have to account for the fact that you already have this distance of 1. Because x equals minus 1. You're not going to count it from minus 1, you'll count it from 1. A positive 1, because dimensions are always positive. Inner radius from this 1. Let's look at the inner radius. It's going to start from a 1 because we're 1 unit away from our reference vertical, which is our y-axis, right? 1 plus the very first curve we meet is root x. But we're looking here at a vertical line of axis. Integration here has to be with respect to dy. You're going to have intervals which are here oriented in a vertical manner. This can very well give you a good representation. 0, 0, and you can have 1, 1. This right here is 0, 0, here's 1, 1. You just look at the y-axis values for your limits, and your limits are going to be 0, 1 along the y-axis. All the equations here should be in the x equals format, because we're looking at with respect to dy. This y equals root x becomes x is equal to y square. X equals 1 is already fine, and this is my other equation. And back to this point, inner radius from our line of axis to the very first curve is y squared, so it's 1 plus y squared. and you know that's going to give rise to an inner area because all these cross-sectional slices are always pi r square. You're going to have pi times this square, which is what? Y to the fourth plus 2y square plus 1. That right there is your area of your cross-sectional slice. Now let's look at the outer radius. The outer radius is from this all the way up to the next line, which is right here, x equals 1. So you're 1 and then another 1 because it's x equals 1. Outer radius is 2. Easy, right? Outer area must be then 4 pi because pi r square, 4 pi. Let's do our volume determination and it won't be hard. Volume with respect to y is equal to, we'll isolate the pi's. See, from these two we've isolated the pi. We're looking from 0 to 1. Outer area minus inner area. 4 minus y to the fourth plus 2y square plus 1 dy. Pi 0, 1. 4 minus 1 is a 3, and then you have a minus y to the fourth, and then you have a minus 2y square, all with respect to dy. This is polynomial integration, not hard by any means. You'll have a 3y minus y to the 5 over 5 minus 2y cube over 3 from 1 and 0. When you do the integration of this, you're looking at nothing more than just a 3, because you're just putting a 1, 0 is meaningless. 3 minus 1 over 5 minus 2 over 3. You know you can do a common denominator here of 15. What I can do is just work this question here on the side and we can post a good answer for you, and we'll post our answer right over here. When you do this computation here, which is not hard, you're going to get this as your answer. It'll be 32 pi over 15, and that will represent the volume of this revolutionary solid that you see. It's a true revolutionary solid with an opening here and expanding here towards the top. There's no point which will stay fixed or firmly bound on your line of rotation. Everything is a distance away from that line of rotation. Hence, you have a circular orbit which pans out in terms of all the points in this solid. This second and last question here will be a good and interesting true revolutionary solid. I promise you a good question over here. We have y equals e to the x, exponential function, x equals 2, a vertical line, and this time the rotation or revolution or the movement is around y equals minus 2, a horizontal line of movement, for which you know your determination is with respect to dx. You'll have horizontal intervals, right? A and b here, intervals will be along the horizontal dimension, and the equations are y equals format, which they already are, the main one especially. How can we go about determining what we're dealing with? Going here through 0 comma 1, y-intercept x equals 2. Imagine this right here is my x equals 2. Nothing here is drawn to scale, alright? And we're looking at this region right over here. All of that. What's my rotational moment? Y equals minus 2. My line of axis, my line of revolution, my line of rotation, however you want to call it. We're looking at that. This is 0 comma 1, this is 0 comma 0, this right here is 2 comma 0, and this here will be what? 2 comma e square, right? You'll just put the value 2 into your function e to the x, it's 2 comma e square. What's my interval? You're looking here along the x-axis dimension. This right here is my interval. My interval is going to be 0 to 2 along the x-axis. And we're doing a revolution here. What will our solid look like? Let's actually get a depiction of this solid. We're looking at something which will be like that here in the upper part of this quadrant, and then it'll be mirrored here exactly by the lower aspect, and it'll look something like this. This right here is a mirror image that develops. You can have, I'm not doing anything too fancy here in terms of representation, but you can see it develops like this. There's this open region right over here. All of this is open region. There's no fixed point which stays fixed onto this line of movement. Everything is moving in a circular movement, as you can see like this. Circular movement. That right there is a revolutionary solid which we have involved here. We have this little funnel shaped opening which goes through and through, open. Now what we have to do is our radii determination, because everything here is regards to the washer. If you do a cross-sectional slice, we have washers develop. We don't have to do anything too fancy here, but I'm just blowing things up over here. Here's my x-axis, here's my y-axis, here's my representation of that, my line of rotation. Going from here to here is my inner radius. From your line of rotation or line of revolution to the first curve you hit is your inner radius, and that right there is my outer radius. I've mirrored this cross-sectional washer with what we're seeing over here. If this is my y equals minus 2, from this you're looking up, the very first curve you see is this right here, your x-axis, which is y equals 0, and that'll come into your inner radius. The next curve you hit right here is this curve coming here, which is your y equals e to the x. So that right there is your top boundary in terms of your outer radius. So you're seeing all of that. Inner radius is from this line of rotation to the first curve, which is your x-axis y equals 0, it's 2 plus 0, which is just 2. Outer radius is going to be again measured from this y equals minus 2. Remember, length is not minus, it has to be positive. That minus 2 is really a 2. Plus this top curve, e to the x. There it is. Inner area. Inner area is going to be this squared, which is 4 pi. Pi r square always. Outer area is going to be 2 plus e to the x whole square. Alright, let's do that. 2 plus e to the x whole square and pi, which will be what? It'll be e to the 2x plus 4e to the x plus 4 pi. This right here is my outer area. You know, volume with regards to washers is always integration with outer area minus inner area, and with regards to whatever. And that's exactly what's going to play in over here. And let's make space and finish this question. We have everything over here now to take this to completion. We have our interval from 0 to 2. We have this right there, inner area and outer area. The pi pushed right outside. Outer area, e to the 2x plus 4e to the x plus 4 minus your inner area, which is a 4 with respect to dx. These 4's will cancel out easily, which will make life very good. You're looking at e to the 2x plus 4e to the x dx. Integrals of exponentials are very easy. It's not hard. We have the integral of e to the 2x giving us e to the 2x over 2 plus integral of 4e to the x is just 4e to the x. Remember, you could have pushed that coefficient out and the integral of e to the x is just e to the x. Simple as that. And going from 2 to 0. Now we have a bit of work to do in terms of this definite integral procedure, and I need to make some room over here so I can elaborate on that for you, and I will right here. The 2's will go in and the 0's will go in here. The 0's are not meaningless when you're talking about exponential functions. You'll have e, 2 and 0 coming into this. 2 times 2 will be e to the 4 minus e to the 0 over 2. This right here is my first part with the upper and the lower interval pushed in. See, the upper interval and the lower interval has been pushed in, and we'll do the same thing right here and right there. Plus, you'll have 4 e to the square minus e to the 0, right? This here is my entire definite integral expression, and I have to solve this out. When I do it, I'll have pi e to the 4 minus 1 over 2 plus 4 e to the square minus 1, and we can do a good numerical answer, which I'll publish right over here. You know, this right here is all calculator work. I take a item over here which I've done on my calculator and this, and I've added them up and I've attached them with the pi. I'm getting a 52.355 pi. If you want to get this into a better numerical answer where you include the pi value, multiply this by pi, and you get 164.48. So we can put right here, the volume is 164.48 units cube, or you can just say 52.36 pi. I'm rounding it up. 52.36 pi. I think this 52.36 pi is a good answer, and I'm comfortable with that. And with that, I bid all of you a thank you and a farewell for this video. We've looked here at a true solid of revolution. It's not a rotational solid. Some people will call it a rotational solid, but it's a revolutionary solid, because in terms of the solid that develops and your line of your movement, there's a orbital or revolutionary movement going about it. Thank you for watching. Have a nice day. Bye.